Okay, here's a thought experiment for you. What if you had to save all of science, but you could only use one sentence? It's a challenge from the brilliant physicist Richard Feynman. And his answer, well, it reveals a single idea so incredibly powerful, it's the foundation for almost everything we know about the world.
But before we can really get our heads around that one sentence, we have to back up a little and ask a more basic question. How do we actually learn about the world in the first place? We tend to think of science as this big book of facts, but the real process is, well, it's messy, it's surprising, and honestly, it's way more interesting. Think about geometry for a second. It's so clean, right? You start with a few fixed rules, a few axioms, and you build this perfect, logical system from the ground up. Science just isn't like that at all. It's this ongoing process of discovery, where every truth we hold is really just our best current guess, our closest approximation. We are constantly testing, making corrections, and just sort of inching our way closer to a deeper understanding. And this all leads to the single most important rule in all of science. The final judge of what's true isn't some brilliant person or an ancient book, it's reality itself. Every single idea, no matter how beautiful or elegant it seems, has to face the ultimate test: experiment. And if it fails, it's wrong. That's it. That's the engine that drives science forward. So that brings us right back to Feynman's incredible challenge. Just imagine some cataclysm happens. It destroys every book, every computer, all of our scientific knowledge is just gone. You get one chance, one single sentence to pass on to the next generation of humans. What idea contains the absolute most information, packed into the fewest words, to give humanity the biggest possible head start? And here it is, the atomic hypothesis. I know, it sounds almost childishly simple, right? But don't let that fool you. In these few words, you've got the secret to matter, to heat, to pressure. You've got solids, liquids, and gases. It's like a conceptual seed from which pretty much all of modern science can be regrown. To really see just how much power is packed into that one little idea, Feynman invites us on a journey. So come on, we're going to zoom in on a single drop of water, magnifying it again and again until its deepest secrets are totally revealed. So at first, all we see is a smooth little drop of water. Let's magnify it 2,000 times. Whoa, okay, now we can see these tiny little creatures swimming around. Pretty fascinating, but not what we're looking for. Let's push it. Let's go to 4 million times magnification. Now the water itself starts to look kind of lumpy, almost like a seething, restless crowd of something. We're getting close. Okay, now let's go all the way to 1 billion times magnification, and suddenly, there they are. And this is the world that Feynman's sentence described. It is a place of pure, violent, non-stop motion. Those are H2O molecules, each made of 2 different kinds of atoms, all just jiggling and bouncing and twisting in this chaotic dance. They're all constantly pulling on each other. That's what holds the drop together. But if you try to squeeze them too close, they push back with an incredible force. This isn't some calm, peaceful pool. It's a subatomic mosh pit. So we have this hidden reality of jiggling, bouncing particles. But how does this invisible, violent dance create the world that we actually see and feel every day? Well, it turns out that simple, jiggling motion is the secret behind some of life's most common experiences. And here it is, one of the biggest payoffs. That perpetual, random jiggling, that is heat. When you put a kettle on the stove, you're not adding some kind of heat substance. You're just transferring energy that makes all its little atoms jiggle around more violently. Heat is simply motion on a microscopic scale. That's it, really. And this one simple idea explains the states of matter perfectly. Think about it. In a liquid, the molecules are all crowded together, jiggling and sliding past each other. Now, add more energy, which means more jiggle, and they fly apart entirely, becoming steam. Now let's take energy away, slow that jiggle way, way down, and they'll snap together into this fixed, vibrating crystal pattern, and we call that ice. Liquid, gas, solid. It's not about what they are, it's just about how fast they're moving. Okay, so this atomic dance doesn't just explain states of being, it explains processes. It explains what happens when things change in the world around us. So let's take a look. Let's take evaporation. Inside that chaotic liquid, some random molecule right near the surface gets an extra hard kick from its neighbors. It gets blasted with so much energy that it literally breaks free from the attraction and just escapes into the air. But here's the really clever part. The molecules that escape are the ones with the most energy. That means the average energy of all the molecules left behind drops. The liquid actually gets cooler. And that is exactly why blowing on your hot soup works. This whole model also draws a really sharp line between two different kinds of change. In what we call a physical process, like boiling water, the atomic partnerships stay the same. The little H2O molecules just move farther apart. But in a chemical reaction, like a fire, the atoms actually break up and swap partners, forming brand new combinations. You can think of it as the difference between a crowd just spreading out versus a crowd totally rearranging itself into new little groups. And just look at the complexity that's possible. The smell of violets, for example, is caused by this absolute monster of a molecule. It's not alive, it has no goal, no purpose. It just jiggles randomly through the air until, by pure chance, it happens to wander into a receptor in your nose. The fact that chemists can figure out the exact three-dimensional arrangement of all these different atoms is, well, Feynman called it one of the most fantastic pieces of detective work ever done, and he's right. So, we've journeyed from a simple drop of water all the way down to the jiggling atom. Now it's time to zoom all the way back out and apply this incredible atomic idea to the most complex thing we know of. This leads us to what Feynman called the most important hypothesis in all of biology, that everything living things do, atoms do. In other words, there's nothing that life does that violates the basic laws of physics. You and I, we're just collections of atoms too, obeying the exact same fundamental rules. I mean, really think about it. A simple substance like water, which is just the same H2O molecule repeated trillions and trillions of times, can create the mind-boggling complexity of ocean waves, the delicate beauty of foam, the incredible roar of a waterfall, all of that from just a simple repeating pile of atoms. And so Feynman leaves us with this final thought. If a simple, repeating pile of atoms, like water, can create so much complexity, what happens when you have an arrangement of atoms that is not simple, that is not repeating, but is instead the most intricate and complex structure we know of in the universe? What might that great glob of atoms be capable of? Is it possible that you are it? A collection of atoms so unbelievably complex that it can actually stand there and contemplate its own existence?